Provo a utilizzare. Non funziona se sono qui, vabbè, non è importante. Ok, ci siamo. Tu non ci sei? Posto?
Quando inizi vai.
Ok, scusate, no, non avevo... Io ci sono. Perfetto. Condivido lo schermo. Ok, ci siamo. Ok, sì, sta caricando schermo. Credo di sì, sì. Ok, perfetto. Tutto a posto, Claudio? Ok. E magari metto in full screen, adesso senza fare pasticci. Oh, I'm already in full screen, okay. Enter full screen. Okay. Not sure why, but we're gonna keep it like this. All right, so first of all, thank you very much for attending the meetup tonight. We're very happy to, can you hear me? Oh, just closer, or go back or forth? Can you, okay, perfect. Yes, so I was saying, welcome. This is the first time that we organize this meetup in Vedrai, so it's very nice to have people from the data science community with us tonight. And thanks to Christina, obviously, for facilitating the organization. We are your hosts today, and we're Vedrai. We work in artificial intelligence. We are an Italian company, and I'll just give you a brief introduction to what we do. If you're interested and want to know more, let's talk, obviously. So we'll have a few people from our team available to have a chat with you, to know what you're doing, and if maybe you might be interested in joining us, because we have a few positions available. So what we do is we apply artificial intelligence to help companies and key decision makers, typically, to make better decisions, to make scientific decisions, and in situations of uncertainty. So we apply what we're trying to build is, to put it in very romantically, but I know that you're data scientists, so I can't amuse you or too much with buzzwords or anything like that. But what we're trying to do is trying to create this envisioning and this prediction engine that allows people to make simulations, come up with special conditions for their own problems and situations, and make these decisions in a way that's more secure, more reliable, and overall better in the outcome. So again, if you're interested in our technology, please... Okay, so we're 80 employees, so we have grown up since we started as a startup, and raised quite a bit of money. So we do have, fortunately, our backing to play around, obviously, with a lot of these technologies that you probably know already. And we love Python. Python is not only the only language, obviously, that a data scientist or data engineer uses, but let's say it's almost like a lingua franca, Latin, so to speak. So we do have positions available for people who enjoy working with this language and its ecosystem. So again, if you're interested, want to know more, want to join us, helping build great products, please do get in touch. And with this, I will leave it to our fine guests from Data Science Milan. And I forgot to load your presentation.
Okay, never mind. I can just go without it.
Yeah, if you can.
Email, maybe, but anyway,
We'll bring it up later.
Yeah,
And
yeah,
let's
no
do it that
problem, no
way
problem,
then in
of
that
course.
case. Sorry.
okay, so welcome everybody. Thanks for being here. Thanks to Christina once again. Thanks to all the team of Vedrai for the opportunity of organizing this event. So today we are here talking about cybersecurity. And actually, it is the first time since a very long time. I need to go there. I know, Claudio. I know. I'm sorry. I'll be here. Okay. So it's the first time since a very long time that we decided to have a thematic event. So tonight we are going to talk of cybersecurity with two different approaches, two different points of views, so we can get a bit more in touch with the intersection between cybersecurity and data science. Just a couple of words about our community. We were born in February 2016, so it's been quite a long journey until now, and the community is now 2,500 people, and is growing every day. And okay, thank you. But I don't think people remotely are interested in my page, but anyway. And so we usually organize this kind of events once a month, and you can find all the details on Meetup application and on Eventbrite, where we publish our events. You can find us also on LinkedIn and on YouTube for all the previous registration of recordings of the sessions. We usually meet once a month, but also in other occasions, like the Pi for AI, where we met a lot of people that are here, that we had in Pavia last Saturday. So it's a ever-growing community, and if you want to join us in writing articles for LinkedIn or just to organize some kinds of event in university or in companies, please let us know. So thank you very much, and I will leave the floor to the first speaker, Luigi.
La tua presentazione? Ah, ok, perfetto. Quindi va bene se la metto così o vuoi aprirla con Lumen? Vediamo se lo apre. Ok. Ok, aspetta, scarichiamola. Poi condivido la... Ok, deve essere a posto. Non so se con lo clicker puoi fare qualcosa. Probabilmente no. Dici con... Ok, provo a vedere se riesco a farlo. Allora, Cybersecurity. Ok. Tu usi Mac? Ok, mi sì. Something being, Claudio, qualcosa si vede la condivisione? Ok. Vediamo se... Ok, puoi scendere giù così. So se... Però qui non si vede molto bene, aspetta. Andiamo a... Prova? Si legge alla fine? Sì.
Yeah. Okay, perfect. Thank you so much. And welcome, everyone. Thank you to Data Science Milan for organizing this event and Vedrai for hosting us today. I'll speak about an application of graph theory to cybersecurity, following along a project I did at university, supervised by Professor Sana Bassino at Imperial College. I won't go too much into the detail of the project itself. I'll try to speak about some general concepts about graph theory and its application to anomaly detection in cybersecurity, which I think are more interesting and can give more ideas. Starting from an introduction, so about myself first. So my name is Alberto. I'm graduating in physics. After that, I worked as electrodynamics engineer in Formula One, and now I'm an artificial intelligence engineer in Formula One. In parallel to that, I studied data science and machine learning, and so I'm going to speak about the research I did in 2023. And we start from a background, the cybersecurity context. So scale and complexity of cybersecurity attacks have been increasing in recent years, and that made it necessary to couple rule-based methodologies with statistically grounded methodologies. Okay. And what are the main challenges when we apply statistics to cybersecurity? The first one is that we need very fast computation. So we might need to study and see the anomaly between thousands or millions even on computers. So we need very fast computations. We also need to reduce the false alarms as much as possible, because if you imagine finding thousands of anomalies which are false, then we would overload the security teams unnecessarily. And also explainability is very important. Explainability is very important in any branch of data science, machine learning, but I believe personally even more so in cybersecurity, because the anomalies are very extremely rare. So it's impossible to say, I believe this is an anomaly because I've seen something similar before, because anomalies change continuously. And for this reason, I believe you need to explain the models and how they work very well in this setting. We have a silver bullet in doing this anomaly detection. Usually, the attackers cannot access the target computer, the target machine immediately, because that is usually very well fortified inside on-premise, for example. So they would try and begin from a liable machine. Imagine an employee working at a coffee shop, right? They can get into the computer, and then they need to move laterally within the network until they reach the target machine, which is C4 in this example here. And by doing so, they're going to leave some hints in the network, which is what we're looking for to find the attackers. Okay. Now, what's the most natural mathematical representation of a computer network? That is a graph. Okay. So imagine we build a graph where each of the nodes is a computer. We've got 5 computers here. And there's a connection between computers if there's been a connection request, say, between 2 computers. So that would look something like that. Okay. We can represent this with 2 possible data structures. The first one is called a adjacency list. It's made of 2 sets. The first is the computer set, which just lists the computers in the network. And the second is the edge set, which is a list of connections, links between the computers listed in the node set. The second possibility is the adjacency matrix, which is an n by n matrix, where n is the number of computers, okay? And you find 0 in the entry corresponding to no connection between computers, and 1 if there has been a connection. Okay, so going forward, the question is, how do we model a graph? So how do we model, for example, an adjacency matrix? There are 2 possible approaches. So we distinguish between global methodologies and local methodologies. I'll briefly speak about both, and then we see an example in local methodologies. When we speak about global modeling of graphs, the point is to find a vector that we can associate to each of the computers in the network. We are kind of trying to uncover a latent space, because we put all the computers, we associate a vector to them. This vector is in a space, so distances between vectors, so between computers as well, has to make sense. Okay. So let's see what happens here. I show one methodology, which is based on a spectral decomposition. Is the Eigen decomposition of the adjacency matrix. So we take the same graph as before. This is the adjacency matrix we saw before. With one line of Python, we can calculate the Eigen decomposition of the matrix. So I've got lambda, which are the eigenvalues ordered by magnitude, and we've got the eigenvectors put in a matrix, U. So some of you might be familiar with this Eigen decomposition of the matrix. And then say that for the purpose of visualization, for example, we want to retain only the first 2 vectors corresponding to the biggest eigenvalues, and we plot that in a 2D plot. Okay, so which is what I show on the right. Let's try and see what happened. So C3 and C4, they end up being associated to the same vector. They are in the same point in space. And this makes sense because they both communicate to C5 and also communicate to each other. So their behavior in the network is exactly the same. Then we find C5, which is close to them both, but is different. It makes sense that it's close. And then C2 is the furthest away. Again, that makes sense because C2, for example, is the only computer that communicates with only one other computer. Okay. So this is just an example. Computationally, for a small matrix like this, is pretty easy. But imagine having like millions of computers, then this matrix would be 1,000,000 by 1,000,000, and doing this calculation might be pretty difficult. Even more so if we move to a dynamic setting, because now I've shown a graph which is static. Okay, But let's say that the graph I showed before is the graph at time t1, bottom left, and at time t2, the connection between C3 and C4 disappears. So C3 and C4 haven't communicated anymore. How do we model this evolution? One approach, which we will see now why it doesn't work very well, is to do the independent embedding as we did before for the two graphs, which is what I show here in the middle. Why this is not good? Because, for example, computers C1 and C2 and C3 in the red vectors are different from the black vectors for time 1. But that doesn't make sense. Let's take C2 as an example. C2 sees exactly the same behavior. It's just connected to C1 in both cases. So having a different vector for C1 doesn't make sense. In general, we want two stability properties when there's time evolution. We want to find computers that behave similarly close to each other at any given time, and computers that behave constantly through time, we want to find them in exactly the same position through time. Okay. So, for example, an approach that works, I'm not going to go into the detail of it, is, for example, omnibus embedding. And as you can see, this approach leaves C1, C2, and C5 in the same position, and we find C3 and C4, which are the only two computers changing behavior in a different position, down here. And we still find them together, which also makes sense because, again, they both behave the same. They both communicate only with C5. Okay, let's see now local methodologies. Okay, local methodologies, as you might imagine, have to do with like choosing a computer, like sitting on a computer and seeing what happens to this computer, what other computers communicate to it. And by definition, has to be a dynamic approach, because if we like restrict ourselves to only one computer and we take a static setting, we don't see much. So it is by definition dynamic. And so we have a list xi, yi of connections between two computers x and y at time t. We can plot that on a timeline. And going local means choosing a computer. In this case, I choose computer y2, which is the computer in blue here. And what we try to do is to model the sequence of events that this computer receives. In this example, is a request, connection request, authentication request, say, from computers x5, x3, x5, and x2. So the question in the local approaches, and there are many different ones, we'll see one right now, is how do we model this sequence of events, and how do we then predict the probability for what is coming next? Okay. So the approach I'm going to speak about is a Bayesian approach, a Bayesian non-parametric approach. But we start simpler because it's easier to then understand the Dirichlet process that we see next. So what if we thought about modeling this sequence of events with a histogram? Okay, so we build a histogram, and we say naively that the probability of seeing computer x2 again, because we've seen it only once, is 1/4. Okay. This histogram approach wouldn't work for two reasons. The first one is that histograms are meant to describe probabilities, to estimate probabilities, not to like calculate predictive probabilities. So in general, asking the probability of x2 given the histogram is meaningless because there's not a modeling assumption. Say, for example, you know a priori that x2 can appear only once, then no matter the histogram, the probability of seeing it again is 0, right? And also, how do I define the probability of something I haven't seen before? For example, what's the probability of computer x1 given this histogram? We don't know. Okay. So here is where the Dirichlet process comes in. We can call it, Professor Romani used to call it glorified histogram because it's a slight variation of it, although the theory behind this is quite complicated, but it is intuitive to explain. So in the Dirichlet process, we say that the probability, so we postulated the probability of seeing a computer X asking for an authorization request, given the sequence of computers we saw before, is proportional to alpha if the computer has never been seen before. So we solved the first problem. It's otherwise is proportional to the number of times we have seen that computer before. So the second line is pretty much the histogram we saw before. So in the example from the sequence that we were trying to model, the probability of seeing x2 again is proportional to 1, x3 proportional to 1, x5 proportional to 2, and x1, which has never been seen before, is proportional to alpha. And the good thing here is that now we have like a formal model, and we can calculate predictive probabilities and also p-values. I'll try to show with a simple practical example how this works. Let's assume for the moment that alpha is smaller than 1. Okay, so at the beginning, the computer Y hasn't received any authorization request. So the histogram on the right is empty, and the probability of seeing X, which means seeing anything, is 1, because anything we receive is just what it is, right? If we see X1, okay, then we calculate a p-value. The p-value in this sense is what is the sum of the probability of seeing events at least as extreme as X1. In the first case, anything is as extreme as X1, so the p-value is 1. Then next, we populate our histogram. And because we now populate the histogram, we can expect X1 to appear again with probability proportional to 1, anything else proportional to alpha. Then we see X2. Okay, so now what happens? What is as extreme as X2? Because X1 is less extreme, anything that is at least as extreme as X2 is everything else, so alpha over 1 plus alpha. We populate the histogram again, we calculate the predictive probabilities, and when we observe, say, X1 again, the p-value now is 1, because X1 is one of the most probable computers, so anything else sums up to 1. Last step, predictive probabilities again, we see X2 again, and now the computer X2 is like in the middle, so X1 will be more probable, so X2 and all the rest together sum up to this value. And now because we have p-values, the smallest p-value corresponds to the most anomalous compute connection we have received, the connection request we have received, which in this simple example is 0.47, is when we saw X2. Okay, now imagine doing this for all the computers in the network, and then you can join the p-values together and come up with a score for each of the computers in the network. You take the smallest one, or you order them, you rank them in order of p-values, and so on top you find yourself with the most anomalous computer. These are the computers you would pass to the security team for further checks. Okay. So in conclusion, for the first part, we've seen the global models, how distances in the latent space make sense. There's a problem though, these are user difficult or computationally expensive, and also when you go dynamic, you need to have some stability properties which are usually not very easy to satisfy. Local models, on the other hand, are simpler to compute, better scalable, and suitable for distributed calculations. We saw it before, it's a matter of doing a few sums, like many few sums. And in particular, we focused on the Dirichlet process, which we saw is intuitively not much more complicated than a histogram, is simple and fast to compute, and also pretty easy to explain. Okay, now we move on. We have done a local approach first. What is a potential problem with a local approach? It's related to the fact that we don't see what else happens inside the network. So imagine that today I have a computer, which is a personal computer, and tomorrow the IT department decides to change its destination of use and becomes a server. Okay. From the computer point of view, because before it was seeing not much activity, today it starts to see a lot of activity, and from the computer point of view, this is anomalous. But then if we compared what happens, so the behavior of this computer with other computers inside the network, actually would see that this behavior is pretty similar to any other server inside the network. So you would tend, by looking at what happens globally, you will tend to lower the anomaly level for this computer. And this is exactly the point of the second part. It's about finding a way to reduce the false alarms from the first part of anomaly detection by comparing the communication pattern for potential anomalous nodes, potential anomalous computers as flagged by the first part of anomaly detection, with a common or average behavior that we see inside the network, to have a refinement of the ranking of anomaly. Okay. So if the computer is very anomalous according to the local method, but its behavior is on average present inside the network, you lower the level of anomaly. To do so, we need to define, first of all, the neighborhood of a potential anomalous computer. So the neighborhood of a potential anomalous graph. Okay. And then we need to decide how to model what is a common behavior in the network, which is not easy. And it has to be statistically grounded, because then we want to be able to calculate probabilities and p-values to combine these with the first part of anomaly detection, the local part. Okay. So what was the solution to this? To the first part, so how to define the neighborhood of a computer, anomalous computer, we see it here. So imagine this is a zoom. Imagine this huge graph with millions of computers. We just zoom in this region, at the center of which there's an anomalous computer with the p-value of 0.01. I colored it red. And we want to see what happens in the neighborhood of this computer. For example, I define the neighborhood as the set of computers that can be reached from the red computer with 2 steps. Okay, so for example, I can get to the green, I can get to the orange, I can get to this other orange, to this other green, and nowhere else, because going, for example, to this red would take 1, 2, and 3 steps. Okay, so this is what happens. I define the neighborhood of a computer. Then what I do in training, I create subgraphs of the big graph in this way. So for each of the computers in the network, so I've got millions of these subgraphs, and I want to show this to the model so that the model learns on average what happens inside the network. When I deploy the model, instead, I would calculate these subgraphs only for the anomalous computers, as flagged by the first part of anomaly detection, and pass these through the model. If the model works well, it means that the model has seen this graph or similar graphs before. If the model is complete bullshit, it means that this graph is anomalous to the model. Okay. So the point in the second part is that we don't, if we've got millions of computers, when we deploy the model, we don't calculate the subgraph for millions of computers, but only for the top 100 or 1,000 anomalous ones. Okay. Now, the second point, how do we find a model which can learn the average behavior within a network, and also is a probabilistic model, so we can calculate probabilities and likelihoods and so on. So the solution I went for is a graph variational autoencoder. I think I've seen autoencoders in one of the previous session, a previous meetup. This is pretty similar to what we've seen. It's just different in the sense that the input is the adjacency matrix of a graph. Okay, so you enter with this adjacency matrix. Then you have a series of neural network layers, which are specific for graphs, specifically designed for graphs. The output of these are some vectors. Okay, we have, in this case, a couple of vectors for each of the computers that build this adjacency matrix. So we've got 5 by 5, so we have 5 computers. Each of these computers has a set of vectors, which we use to parameterize a probabilistic distribution. This is typical of variational autoencoders. Then we sample from this distribution a vector for each of the computers. And then what we do, we build back, we try to build back the adjacency matrix by multiplying, taking the dot product between vectors zi and zj for each of the entries ij. We pass it through a sigma activation function to have it between 0 and 1. Why do we want to have it between 0 and 1? Because we want to interpret the output for each entry as the probability of a Bernoulli distribution. So those of you that are familiar with images, so this is pretty standard when we do like images, variational autoencoders for images. Imagine the input is an image, a black and white, 0 and 1, and you try to build back the image with a Bernoulli matrix as well as you can. And the point is that by showing in training millions of graphs, of subgraphs from the network to this model, and trying to be able to learn how to build back the adjacency matrix the best possible way, then your model in the probabilistic embedding, the lower dimensional probabilistic space, is in fact learning what happens on average inside the network. So then when you go into the inference, so you take a subgraph that you think is anomalous and you want to check whether it is or not. This subgraph has never been seen before by the model. So you pass it into the model here. Okay, everything is fixed because all the parameters that we had here were learned in training. And we get a Bernoulli matrix out. And if the Bernoulli matrix that comes out is similar, okay, we can calculate with the likelihood or with a p-value, is similar in some sense to the input, then it means that the input we passed it through has been seen by the model before. If the output we get is complete bullshit, then that graph is anomalous, hasn't been seen before. So this is the idea. So I tested this approach on a dataset, which is called the Los Alamos National Laboratory dataset, which is freely available. I took a subset of it because it's huge. And even with a subset, it took me 40 days on GPU to train the model, because there's many of these subgraphs, really, really many. But then in inference, as I said, you test, so you pass through the model just a few graphs, the ones you think are the most anomalous as flagged from the first part of anomaly detection, and you can also parallelize this calculation. So in inference, it's pretty fast. What I got were mixed results. So in some cases, I could reduce the number of false anomalies. In others, I couldn't. So there's definitely scope for improvement. Yeah, there's one. Okay, here on the right, we have some examples, some practical examples. These are graphs which are 35 by 35. So there are 35 computers in this subgraph. So you have the adjacency matrix, which is indeed like an image here. You pass it inside, and you get a Bernoulli matrix as an output. Okay, and then you use this Bernoulli matrix to calculate the probability of the input given the Bernoulli matrix. A thing that is a problem, I believe, with this approach is that it lacks from explainability, because we have a model that learns the average behavior of the network. So I could go to the security team and say, look, the local approach told me that this computer C1 is very anomalous, but the second part actually tells me that this behavior is already present inside the network. Then what if the security teams ask, well, where is it? Where can you find it? Show me. Give me 10 examples of computers that behave similarly to this computer that you say is no longer anomalous if you look globally. And that is very difficult to say. Okay. So this is the problem I see with this global approach. Okay. So this is pretty much what I wanted to say. I conclude with like two facts, which I think are interesting. The first one is the Gartner hype cycle for technologies. So the idea here is, so I want to show what I talked about today, where it places itself in this cycle. What's the idea here? That, well, somebody has an idea, there's an innovation trigger, okay, then there's a hype, so like everyone starts like building things with it. Then there's people realize it's not sustainable in the long term, so the investment drops down, the disillusionment part, and then at some point it plateaus to productivity. To give you an idea of something that we all know, like generative AI at the moment finds itself in the peak of hype, right? We also find graph data science here and generative cybersecurity AI. So what we spoke about today, and according to Gartner, we expect them to plateau between from 5 to 10 years to now. So probably they will be at their hype in 2 to 5 years. And the last thing I want to say is, if you're interested in cybersecurity or just worried about cybersecurity threats, I think there's a very interesting report by ENISA, which is the Foresight Cybersecurity Threats for 2030. I'm not going to read through all the points here. It's very interesting. I suggest you read it. I grouped it in 3 areas. So I think we will have more and more threats coming up because software and hardware maintenance is difficult. So we're writing so much software right now, and also like thanks to a lot of help we get from generative AI, we read like tons of code, and it's very difficult to maintain it and keep it safe. Then, of course, the complexity of the attacks will increase because like attackers will start already use generative AI as well. And also we're giving away a lot of personal data, which means that in the future, attackers, even if not just already now, they will craft like attacks which are specifically built for us as a person, right? So it will be more and more difficult to find them. Yeah, so we need to all get involved with cybersecurity and find good algorithms. Right. Okay, thank you very much for the attention, and I leave it to Luigi. Any questions? Yes, I have one. Yeah. Okay. May I? Yeah, it's.
Okay, I forgot about it. Let's go through the next question.
Okay. Okay.
First of all, thank you for your presentation. It was really good, and I'm quite far away of cybersecurity, but it was a really comprehensive. My question is about the model. As I understand, you use machine learning model for searching anomaly detection, and I was wondering how you train model in sense. You should be sure that there is no anomalies when you train model to find them.
Okay.
Then how was you sure about your data?
Yeah. Thanks for the question. It's a very good question. So I'm pretty sure there are anomalies in the data set when I train the model, because you very rarely know when something is an anomaly, okay, and it's impossible. So like some anomalies pass through. So and you like labeling doesn't exist pretty much in cybersecurity. It's very difficult to label the data. So when I train my model, For sure, there are some anomalies inside. So the model is also learning the anomalies. The point is that hopefully these are very rare, and also they change in their shape with time. So like you might see one anomaly with that form just once or twice, but then you've got millions of other computers which are normal. Okay. So yes, we're not 100% sure, and I might say we know for sure that there are anomalous computers also in the training set. Yeah, we rely on the fact that there should be very few.
But for existing of anomaly, some some hack must be in this network, no? Because like as I understand it, anomaly like exists if any like hacker activity in the network starts.
Yeah, for sure.
Okay, so in this data set, someone like can do hacker activity or like did some hacker activity. So he on purpose created anomalies.
Yeah, so in the dataset I used, so in this dataset from the Los Alamos National Laboratory, yes. So this is a famous dataset for cybersecurity studies because there is a known anomaly.
Okay.
So like companies have got red teaming teams, and they create like fake events on purpose to like test how the network reacts, how the system if the system is solid and can react to anomalies. So in this case, there are known anomalies, and this is how I tested how well my model did, because I knew of some anomalies. But still, despite knowing what are anomalies, there might be other anomalies. So I know the anomalies from the red team, but I know that there might be other anomalies that I don't know, right?
Okay.
Still, there's for sure more anomalies than I think there are.
Okay. Thank you.
In general, if say you have like your network and your network doesn't get attacked by anyone for like months, okay, which I believe is unlikely, but say like theoretically, this is why having a second global anomaly detection is important, right? Because if you used only the local approach, then you will still have, say you decide to look at the first 1,000 computers, then every day you still have to look at 1,000 computers, right? Because you don't know, you cannot compare it with anything else you've seen before, right?
Yeah.
Whereas if you use the second part of anomaly detection, hypothetically, if there are no anomalies, you can go and say, look, no, of these 1,000 anomalies today, I don't believe any of these is worth looking at, right?
Thank you.
No, thank you for the question.
I also have another question. So thanks a lot for that. To my understanding, I understand that your local approach is time aware, so it takes time into account. But to my understanding, the global one is not time aware, does not take the time evolution of the network into account. Do you think that like another regressive approach, where instead of just passing to the GNN a single adequacy matrix, you just pass the sequence of the last three, would help your approach?
It's a very good question. For sake of simplicity here, I showed it as a static problem, but in fact, I treated it as a dynamic problem. So I don't know if I put a slide somewhere hidden at the bottom. So yes, there exist variational auto-encoders for dynamic graphs. And hopefully I have an image of it here. Okay, no, I don't. Okay, so the point is, let's go back to, I answer very quickly because I don't want to take too much time, but oh my God, where is it? We're almost there. Yeah. Oh, okay. Okay. So in this static setting, so something I haven't shown here for you that are for those of you that are familiar with variational autoencoders, you usually have KL divergence loss as well. So you have the loss between the Bernoulli matrix and the input, but also something I didn't show here for sake of simplicity, which is the KL divergence. So imagine for people who don't know what it is, imagine having another distribution here that I compare to, and I don't want my distributions to become too dissimilar from this reference distribution. Okay. So there's a paper where they translate this static approach into a dynamic approach, and they do it by putting LSTM. Actually, I think they use the GRU, gated recurrent unit, on the prior, okay, of these distributions. So basically, imagine having in my project I used 4. So like I looked at like 4 time steps for each of the graphs. I would have like 4 of these, and these are connected by the prior that changes with time with our gated recurrent unit. Yeah. Thanks for the question.
Okay, sorry guys, I was a bit shy. So my question is, did you train it against some real world traffic, right? Some pickups or?
Well, this data set is real data from the Los Alamos. So the Los Alamos National Laboratory is real data from the Los Alamos National Laboratory in the USA. But other than that, no, I didn't try it on other networks. It's usually very difficult to have access to network data to do this kind of analysis.
And sorry, were you able to identify use cases in which it helped to prevent false positive? Use cases in which it is pretty much useless?
Yeah. You mean the second part? Yeah. So like I had to. There were 2 anomalies in the network because I took a subset, as I said, because like the whole data set was huge and it didn't have more than 40 days, unfortunately, to train my model. Okay, so like the first part of anomaly detection. Okay, by the way, because we're speaking of the data set, so like this is what the data set looks like. So we've got like millions and millions of lines where the first is the timestamp, and then I have like a connection request between 2 computers. So like 1250 asks for connection to 506, and we've got like millions of these. So the Dirichlet approach I showed in the first part, for these 2 known anomalies, so these are like anomalies that we know of, like ranks them to position 304 and 581 out of millions of computers, so it's good. Then what I did in my project was to like extend it, so I didn't speak about that, but there's another process which is called the distance-dependent Chinese restaurant process, which, yeah, Chinese restaurant process, you heard well. Yeah, it ranked the anomalies higher, so that worked. Whereas the second, going to your question, the second part of anomaly detection, which aimed at reducing the false alarms, had a mixed results. So like for one of the 2 anomalies, I ranked it much higher, like 19. The second one, unfortunately, didn't get any better. Actually, pretty like slightly worse, I'd say. So there's mixed conclusions. But yeah, there's a lot of work to do if someone wants to use this approach. For example, the training I had to stop it after 40 days because I had to graduate at some point. But yeah, it was still learning the model. So and for example, another thing somebody could think of is removing the servers from this data set, for example, because servers communicate with a lot of computers, so they produce like huge graphs and you lose a lot of time there. So like, you know, a priori, for example, that some computers are servers and you look at them separately. So there are possible things that can be done. Yeah. Did I answer your question?
Yes, I have more, but I don't want to take too much time with others, so I will ask you later.
Okay, yeah.
Thank you for the presentation. I wanted to ask, well, you answered to my first question, that was why did you choose to stop training after 40 days? I mean, I wanted to know if you would use some like methodology to say, okay, that's it. But you answered me. The second question is,
yeah, there was an early stopping set, but yeah, never got to that point.
Okay.
I had to kill it before.
Okay. And the second question is, since it's a expensive process to train a model with a GPU for 40 days, did you take some cautelative approaches to say, okay, my training process is safe, it's correct, so it's gonna learn, it's gonna converge at some point, or?
Well, yeah, what I did mainly was to monitor how it did in the beginning. So like I started with like much smaller. So first I started with a much smaller data set, like that would train in probably like three days. Yeah? Like I started with something simple. And then when I jumped onto the big data set, all I could do was like monitoring the behavior like day after day. And when I saw it was doing something sensible, I was happy with it. Yeah, of course there's a lot more that can be done to make it better. Also in terms of monitoring, right? Because as I said, if I was to do it again, I would remove the servers, for example, from the training set, because the security team already knows which are the servers, and it's worth looking at them separately. In general, what I found during this research is that one single approach for all computers is a bit of a stretch, because like you have computers that are servers, you have computers that are like personal computers, computers that get, I don't know, like used like once every 2 years. So you might want to like cluster the computers first for areas, and then take like specific approach for each of them. Yeah, a link to that, you said, yeah, the training is long. So the idea for this algorithm in production is that you would train it maybe once a year, maybe once every 6 months, because the assumption there is that the average behavior, so what your users do changes a lot more slowly than anomalies in the network, right? So the idea, because as I said, fast computations are very important in cybersecurity, and this is definitely not a fast computation, the training. So but you would do it like once a year or once every 6 months, and then all the rest of the time you use it on in inference, which you can parallelize and do very, very quickly.
Thank you.
Yeah, no problem. Thanks for asking the question.
Thank you for the presentation. And I'm a little bit confused about the definition of anomalies. I understand that a matrix is passed back to model, and model return like try to build this matrix.
Yeah.
And how you understand where is anomalies? Or is there in this like
Okay.
in this set an anomaly?
Yeah. Okay. So if thank you for asking this question, because yeah, I knew this part would be pretty difficult to explain in a couple of minutes. So the idea is that when in training, like you build back this matrix in the best possible way. So imagine that here I got exactly this matrix, then my model would be perfect. Of course, you cannot learn all the millions of networks like perfectly. So this is why we use like a probabilistic matrix after all. And so in training, I assume everything is, so I assume most of the matrices are good. I know that some are not, but I assume most of them are. So I have confidence that I would learn the average behavior. In training, what is an anomaly? In training, when I deploy the model, an anomaly is a graph that passes through the model here and gives a matrix here that is completely different from the input. So because the model is a model that by its job is to reconstruct adjacency matrices, if it is not able to reconstruct an adjacency matrix, the assumption there is that it has never seen it before. Mm-hmm. So in this way, I define an anomaly. And this is like, can be formally calculated with like likelihoods, for example, or like p-values for the matrix. So I can actually quantify how anomalous the computer is, this network is compared to the model.
And you understand that there are some anomalies in the connections, but it's difficult to identify which computer is like behave anomaly.
Well, it is not because of how I build the network. So I build the network, in this case, centered around a computer which I know I want to test for anomaly. So I choose, for example, the red computer, which I believe from the local approach it is anomalous, and I look at what happens in the neighborhood of this computer. Then, okay, if you're referring to, can I find which is the computer the attacker got into from? No, I cannot, right? Because, for example, in this case, okay, say that the attacker got into this green computer, then for some reason I detect the anomaly here, because what the attacker does moving around the network is very anomalous, is what happens there. So yeah, I wouldn't know which computer, from which computer the attacker entered. No, yeah, thanks. Mm. All right.
I think we can move to the next speaker.
And we'll take a quick break.
Yeah.
So we'll allow him to prepare.
We can have a couple of minutes break.
Yeah, also 5 minutes. If anybody wants to use the toilets, they're just behind there. Feel free. And we do have some refreshments. Grazie. Prego. Sai che perché mi sono Sure.
Aspetta, no, infatti, scusa,
Tu cosa usi
mi-
esattamente? La quella italiana?
Sì.
Ah, ok, così.
Ah, ok, quindi. Vediamo se è così. Ok, forse stavolta è andato. Forse si sta caricando di più delle altre volte, quindi penso che sia giusto il tempo di caricare.
Siamo connessi.
Sì, no, beh, adesso deve caricare i modelli, quindi cioè, un minuto ci mette. No, il fatto è che sì, prima ho visto, non ho fatto poi in tempo perché ho visto che c'è proprio così. Devo proprio di un paio di libri da installare. Che è successo? Ah, vero, cavolo, sì, c'è anche quest'altro.
Poi qui durante la presentazione ci sono del desktop o hai bisogno solo di Streamlit?
Solo del desktop. Cioè mi serve solo
del
del
desktop? Serve.
sì, per quanto sarà il locale, cioè sarà sul...
No, questo non è collegato. Questo proprio non è collegato. Senti bene? Sì, il microfono di macchina.
Ok. C'è qualcos'altro? Sì. Ma che vada... no, infatti. No, infatti ora provo, ma che vada a taglio. Cioè, non è un problema. Era giusto, ecco. Ah, è giusto. E poi scusa, però io i file ce li ho. Ah, cavolo.
Sì, scusami, aspetta, non so cos'è, perché qui è il file system.
Ok, sì, è giusto,
Dove ce l'hai dentro?
Sotto source.
Sotto il source?
Ah, no, aspetta, questo il modello è proprio accanto. Cioè nella stessa
Ok,
direzione.
quindi puoi usare questo.
Ok, sì, perché
Questo deve essere a posto.
non credo che altro ah no, forse qui dentro. Scusami, qui invece credo referenzia le cartelle, vedi qui ci sono.
Ah, sì, scusa.
Ci sono questo file qui che è sotto source.
Sì, sono tutti i path units da sistemare.
Ce ne dovrebbe essere altre due, quindi questo qua è l'altro.
Sì, poi per complicarti ancora di più la vita uso Vim, i bindings di Vim, quindi lo disattivo se devi utilizzare. Ecco, adesso si comporterà normalmente. Ok.
Quest'altro qui.
Ok.
E ce ne deve essere poi un altro soltanto perché erano 3 file. E poi c'erano un po' di.
No, forse ho fatto forse meglio riabilitarlo. Questo è un motivo.
Vedo che vada, non è un problema, cioè è giusto così per rendere un po' più interattiva. Visto anche là, io ho detto magari faccio qualcosa che fa mostrare, però niente.
Ok,
credo ci siano più problemi perché penso sia solo per questo punto problema di. E poi più giù ce n'è un altro sicuro.
F. E, ok, questo dovrebbe essere a posto.
Sì.
Names. Mi torna questa cosa qui. Aspetta, CSV. Ok.
Ah, forse vuole il doppio. Ok.
Vuoi provare?
Sì, credo che ci fosse un altro file. Quindi ci sono. Ups. Eccolo qui. Devo togliere.
Sì.
L'ultimo questo. Giuro che è l'ultimo.
Ah no, tranquillo. No, io però ho il problema diverso perché non ci vedo pochissimo con questi i caratteri sono bassissimi. Sono piccolissimi.
Ok, adesso deve andare perché era l'ultimo. Ah. Beh, se va adesso è bene, se no pazienza.
Ah, grazie. Ovviamente l'hai rimesso.
No.
No, ce n'è un altro.
Ti ho dato il mio computer con caratteri piccolissimi, dei keyboard layout diversa e key bindings BIM dentro.
Sì, ci sono problemi di scrittura del patch perché ce l'avevo fatto su Windows, quindi è diverso. Posso andare a ritrovarlo. Ecco, l'ho trovato. Di com'era? C'era un altro patch che mi ho dimenticato.
Sì. Vedi che siccome ci sono i key bindings Vim e quando lo disattivo c'è qualche problema, quindi mi tocca fare da interprete. Vim è una bruttissima macchina.
Adesso di controllo.
Sì. Fa queste cifre.
Si traduce proprio il sistema operativo.
Noi eravamo quelli che invece
Userà cos'è? OS Line Set. OS Line Set. Vediamo.
Comunque in caso mi servirebbe tanto il browser, che alla fine faccio tutto da qui, quindi la presentazione sul browser, giusto? Ok, grazie.
Niente, allora facciamo così.
Tanto mi serve solo quell'interfaccia, quindi...
Cosa ti serve esattamente? Cioè, ti
Solo
serve...
lì, basta, perché tanto
ti metto
lì, insomma, è solo
dopo le altre cose e poi tu hai una presentazione.
Sì, faccio prima la presentazione e poi la demo sta alla fine, quindi parto con quella e poi alla fine...
Perfetto, allora qui siamo a posto, sistema questa parte, mettiamo su Data Analytics, poi sei libero ovviamente di utilizzare gli altri servizi visto che ci sono. Questo 9, era giù, questo siamo a posto.
Ok. A questo punto posso essere risposto poi di...
Beh, sì, puoi spostarti perché adesso condivido lo schermo. Anzi,
ok.
Tu hai bisogno di PyCharm?
No, solo
di quello. Allora faccio solo...
Sì, direi che va più che bene.
Ok. E quindi qui dentro... Però l'unica cosa è che quando tu condividi, stai condividendo tutto proprio, no? Quindi andando in modalità presentazione... non so cosa ti faccio vedere. Cosa vedi esattamente?
No,
ok, perfetto.
Poi andiamo avanti con questo. No?
Allora vediamo.
Ok, adesso sta.
Allora, attenzione a questo pellato.
Sì.
Ho visto il prima.
Infatti ho visto... Ok. Hi everybody, my name is Luigi. I'm a data scientist at Data Reply, and the speech presentation that I later put here tonight will speak about the approach of data analytics in field of cybersecurity with its improvements with respect to the traditional cybersecurity methods. I will go through analyzing which are the main challenges of the traditional cybersecurity methods. Then I will explain why introducing a data-driven approach in cybersecurity field is a very good solution that will become more and more useful in the next few years with some benefits that I will show with some use cases, starting from some common situations, going through some use cases that are more less known, but that are even they're becoming more and more important. And then we go through some conclusions. So first of all, which are the problems that the traditional cybersecurity methods have to face? First of all, our traditional methods are based on static defense methods. They are based on signature-based methods that are based on known pattern and pre-built rules. So they are not capable to adapt to the ever-evolving threat landscape, and the attacks that are becoming more and more sophisticated in these years. Then there is also a problem of limited visibility and scalability in today's world. And the most important field is the lack of cybersecurity teams. So I assume in lack of comprehensive monitoring, because in today's world we have all the data that we need to face the cybersecurity problems that are evolving in day by day, but the traditional methods aren't able to integrate all these data sources, and they are not able to understand and face the problems that are and the threats that are ever evolving and becoming more and more sophisticated. And the third point that is related to the second is the high false positive rates, because the traditional cybersecurity methods may raise more alarms than necessary. They are, as Alberto said, there are many false positives that stress the cybersecurity teams, because, as I said, we have a few people to analyze all the data and all these false positives, and they may overlook what the real threats, because they have to spend time by analyzing alarms that are obviously false positives, because there are so much complexity and noise in the data and in traditional methods. So what we need is a solution that is capable to evolve in time, reducing the effort on the security team, the so-called blue teams, being able to detect attacks that are growing and changing time day by day, and we need to take in consideration different data coming from different data sources. So we have to adopt a data-driven approach in the cybersecurity field. Which are the benefits that big data and data science field bring to cybersecurity? First of all, we are able to analyze and monitor millions of events automatically in real time, and we can integrate data coming from data sources that are different and are heterogeneous. And with the help of machine learning methods, we can reduce the false positive that can help security teams in analyzing which are the real anomalies in our data, in our network, because we know that our networks are attacked day by day, but we need to focus on which are the real anomalies, discarding all the false alarms that our traditional and today methods raise every day. I make a simple architecture of what can be a cybersecurity flow based on data analytics. The starting point are all the data sources that in a network could be the servers, endpoints, network devices, firewalls, the user activities, and all of them generates millions of log and events, as I said. So what we can do is to build rules that are not based on the old instance, on the past instance, or not only on them, because if we base only on the past events, we wouldn't be able to face the evolving trend landscape. But we need to build rules that are able to learn from data that are generated from our data sources, and so build rules that can adapt to the environment that changes every day. And we can create, I said, one-to-one rules, so rules that can match a pattern to a specific attack, anomaly, or threat in our network. Then, with the help of the data science, with the AI, we can reduce, as I said, the number of false positives. But another thing that we can do is to prioritize the alarms, helping the security teams not only to reduce the false positive, but saying which alarms are more problematic, can cause more problems to the assets of an organization, for example. Helping them to not overlook real problems and real threats. We can reach a good automation emulating human reasoning, and with continuous learning, we can keep our models up to date with our data and not focus on past incidents, past data. So after applying our rules on log and events and generating alerts that are symptomatic of incident, the last phase obviously is the investigation. We can do all the analysis that we need, but the important thing is that we can provide quick response to the attacks, because the real goal is not to go one step ahead of the attackers, because the defenders are always one step behind, because we react to an attack that is in course in our environment. But we need to close this gap between the attack, the detection of the attack, and the response. And with different data visualization tool, we can have also good capabilities of data visualization. Here I make a simple schema that we saw in some of use cases that we created. For example, the detection of some simple attacks as like past hash or past ticket that are attacks very common in the network. The situation is always when an attacker tries to infect an host that become victim. Every host in the network, as I said, generates millions of logs and events, and we can store them in a data lake that helps us saving data that are heterogeneous. And these log files will be the input of our machine learning pipeline, and with common steps of data preparation, feature extraction, we train our models, and we can say that if a record is symptomatic of an attack or is a benign record. These are only some example of data lakes, depending on the solution that we can adapt. If we have an on-prem solution, we can go through Cloudera or no cloud with AWS or Databricks, but these are only some examples. Then the most interesting part of this presentation, the use cases. I will show only 3 use cases. The first 2 are most common: web and malware detection. The third one is a racing problem nowadays. Web stands for User Entity Behavioral Analytics. In this case, what we need to do is to identify anomalies in the behavior of the users and the entities in a network, for example, the host. So with non-pattern detection and advanced correlation, we can identify and raise alarms if we saw some if we see some anomalies in the user activities. How we can build our solution. First of all, we create a baseline that helps to describe the normal user activities, the normal entity activities. Then we can create an anomaly detection model that can be one of the most common, like isolation forest, auto-encoder, because in many of the use cases that we saw, the algorithm that we choose is important, but the most important thing is the data, the quality of the data, because if we have data that can describe in this case the user activities in the best way, it is not important which model we choose. So with model we can monitor in real time the activities of the user and the entities, and then we can identify activities that deviate from the standard behavior of a user or an host. Malware detection is another very common use case. With the data-driven approach, we can also, in this case, improve the accuracy with respect to the traditional cybersecurity methods. We can detect threats in real time, and we can reduce the false positive rate. How we can do in this case? First of all, we have to analyze the file patterns. We have different ways to analyze the files with behavioral analysis. We analyze the behavior of the files. With signature-based analysis, we analyze the files based on the signatures of known malwares. There is also another analysis that is based on images. We can transport files in images and then analyze them. Also, in this case, we create an anomaly detection model. We monitor the files, and we can classify them as benign or malware based on their characteristics and their behavior. The third use case is DGA detection. DGA stands for domain generation algorithm. With this algorithm, the attackers generate large sets of domains that are used to communicate with their command and control servers. And these domains will be the vehicle for the attackers to transmit their malware or their malicious software they can build. With this solution, we are able to recognize domains generated from new algorithms, because also in this case, we can train our model on past domains that we know are created from domain generation algorithm. But the problem is that these algorithms are changing every day, and they can be an evolution of a past algorithm, or there can be new algorithms. So with this solution that I will show with a demo, first of all, we create a dataset of real-world domains that can be the most common, like Google, Facebook. So the most common domain names and malicious ones. Then we generate the features that are able to describe the domains as text, and then we can identify domain names that are generated from domain generation algorithm. Now we will switch the presentation to the demo just to show how it works. We will see. Yes. This is only just a presentation. For example, if I write an example, domain example, and this exact feature. Our model extract features of this domain. For example, the subdomain word breaker is a flag that tells if the domain is composed by a sequence of words. In this case, over time, a basket are 2 words. So word breaker is set to 1, otherwise would be set to 0. Starts with word tells obviously if the domain starts with an English word, and then there are all the other features like the entropy, the vowel ratio, the digit ratio, if it contains digit, the domain length, subdomain length mean, and then we can predict if a domain is real, is a valid one, or is generated from a domain generation algorithm. If, for example, I write a fake domain, my fake domain dot XSY. So that it could be a possible threat. I wrote this domain this way because an example of domain generation algorithm is an algorithm that generates domains composed by a random sequence of characters and numbers, as in this case. And so I switch back to the presentation. Okay. Eccola, sì. Yes. Okay. So, in conclusion, these words were only some of the possible use cases in which we can apply a data-driven approach in the field of cybersecurity. And why we choose this solution? Because we saw that traditional methods are not capable to keep the pace of the attackers, and these solutions are not meant to substitute the traditional method. They can stay with them, helping the security teams, as I said before, reducing the false positive, prioritizing the alerts, and data analytics can help us in building a cybersecurity posture that is capable to evolve in time and reducing the gap in terms of time between the detection of a threat in our environment and the response, the subsequent response. So we think that it's time to integrate our data analytics procedures in our cybersecurity processes. Thanks for the attention. Do you have some questions? Yes.
Do you have any idea how a red team can use data analytics in their work?
Okay, so an example is are the domain generation algorithm, because we saw that there is a difference between past algorithms that were only random sequence of characters or numbers, as I said before. But nowadays, this algorithm can generate domains, for example, emulating the real-world domains, like a sequence of words, changing them a little bit. And so, obviously, the attackers, I think, but I'm pretty sure that they are using analytics solutions for their attacks, and for this we need to use them to use a data-driven approach also in this case, because as I said before, the defenders are always one step behind the attackers, so we need to reduce the gap, and if we have the means to do that, we can why we don't have to use it.
Yeah, I guess nowadays attackers can use some artificial intelligence to create malware. And for example, on this pentest site, on blue teams can use data analytics to prevent the hacks and detect this malware.
Yes, for example, a solution that we are thinking in these days is a way to understand if a text is built from a large language model or not. It could be a possible solution, trying to detect if text code could be generated from artificial intelligence or not. Could be a possible example. We are thinking of a possible solution like this.
Yeah. Sounds really interesting. Thank you.
Thank you for the question.
Who's curious to know what model was running behind the demo? If it was a gradient boosted classifier or...
Yes, it was the gradient boosted classifier. The detection was the topic of my thesis, and I tried different machine learning algorithms, and the XGBoost was the one that gave me the best results in terms of accuracy and recall. Yes?
Okay, which were accuracy and recall for the model that was classifying domains that you showed us before?
So I trained the model in two ways. First of all, I take the entire data set, I tested it dividing in a random way, and it gave me accuracy more than more than 90%. The second solution, the second validation that I made was to emulate the situation in which the model faces something that it has never seen before. So I excluded some of domain generation algorithms from the training set, and these families will be the testing set. So the model faces domains generated by algorithms that the model doesn't have in the training set. The accuracy falls down to about maybe 86, 87%. But with respect to, for example, LSTM, that was another solution that I tried to do in my thesis. With the first validation, it gives best scores more than 19%. But in the second validation, when it faces something something that it don't have in the training set, the accuracy falls to about 78%. So it was overfitting. It was not able to recognize something new with respect to XGBoost. That is falls. The accuracy falls to 86%, 87%, but there wasn't the accuracy doesn't fall to 70% like the LSTM, for example.
Yes. What are the common features that's usually used in the algorithm?
The feature that I show in the demo, for example, that could be the most common, like the domain length, the subdomain length mean, the vowel ratio, the digit ratio, the entropy. Then I try some features for example, calculating the n-grams of the domains. Or I also tried many textual characteristics that I discarded because they were not helpful in the domain. But all the textual characteristics that can help in characterizing a string could be helpful for the model.
I actually have two questions. One of on this domain analysis. I mean, whenever I build a model, I usually always am very surprised by when I generate a lot of figures. I'm very surprised by what the model thinks is very useful and what I thought was very useful and the model thought that is useless. So, where there did you find example of feature that you were surprised the model used and find very useful, and feature that you were thinking that they could have been very useful and the model thought no?
Yes. For example, in first days, I thought that the entropy would be the most important feature in my model, but it was treated like all the other features. The most important were, for example, obviously the word breaker, because it can discard all the algorithm that generates domains like random concatenation of characters and digits. The engrams also are other important features. The other are useful because I have tested removing them, numbing them, but the most important were them.
And the second question is essentially around use case that you mentioned with the log, analyzing the logs and
yes,
the anomaly detection there. Do you know if there exists already like common solutions out there that do that, or do you think that data analytics is really about customization to a particular company problem? And in that context, how do you think like co-development with your clients or explainability is actually, how much is that important?
So, as per my knowledge, there are also tools that are apply data analytics in the cybersecurity flow, but they are in the early stages, and we are trying to explore as much use cases as possible to see if we can help traditional cybersecurity method. We are novel in this field, and we are trying to explore day by day, finding a new use cases like the one that I told before, a way to distinguish text generated by AI or not. But I think that yes, there are tools that use data analytics. Thank you.
The question is on the model, because you mentioned you tried the LSTM as well. Would you model the sequence of letters in that case with LSTM?
Yes, I tried an approach in the analyzing the sequence of characters, the domains, but for the short time I didn't go ahead in the analysis. I focused on other machine learning algorithms.